Okay, get the focus hot there. Here we go. Page 73, volume 3, we're looking at 18.20. Imagine you have an ice water bath and a reservoir of boiling water, and we're going to connect that with this kind of two material cylinder. You've got aluminum on the left side, brass on the right, and where they meet, I'm just going to call the junction, or the junction there. We don't know the lengths, but we do know that they're equal. And in this problem, we're trying to learn about, well, part A says, which rod conducts more heat, the aluminum or the brass? If you want to take your guess, go for it. I'm going to discuss it in 3, 2, 1. Well, I know that that power is Q over time is K A delta T over L. Now, in this problem, we're going to assume steady state. What does that mean? I think it helps to first discuss not steady state. When it's not steady state, when you first put this in, you might imagine this is at room temperature. This is going to rapidly change to 0. This is going to rapidly change to 100. But then over time, it's going to reach some equilibrium, and there'll be some temperature at the junction in steady state that's not changing. So after you put this in, wait a few seconds, let things equilibrate. Eventually, you're going to fairly rapidly get to a point where there's a constant temperature difference over this one and a constant temperature difference over that one. Now, in this case, the amount of heat transferred by the two rods should be the same. Why? Let's suppose for a second the aluminum was transferring more heat than the brass. All right, so let me go the other way. Let's go this way, because heat is going to generally transfer from hot to cold. So let's say the brass is transferring, say, 500 joules every second, and this was only transferring 400 joules every second. Well, that would mean there's a buildup of 100 joules every second at the junction, and there would be an explosion. So or something would start melting, or some problem would happen. If we really are in steady state, the power transferred by 1 has to equal the power transferred by 2. So maybe I'll say that this way. In steady state, power A equals power B, same heat transfer rate. All right. And I think that was part A. Yes. So we're assuming if they have the same power, they have the same conduction. All right. So part B, what is part B asking? It says, determine the steady state temperature at the junction. So what is the temperature at the junction? So maybe we'll just call this temperature J. And you know what? I'm going to use purple because I know it'll show up better on the camera. My bad. So at some point, right, what is the temperature at this junction? It's showing up okay? No. Temperature at the junction. There we go. Sorry about that. Trying to make sure it's clear on the screen. Well, what can we do? If you think you know what to do, pause the video and try it yourself. I'm going to do it in 3, 2, 1. Here we go. Power transfer for the aluminum times the area of the aluminum times delta T of the aluminum all over the length of the aluminum should equal, etc. for the brass. Now, let's cancel out everything we can at this point. They have the same length. We don't know what it is, but fortunately, we don't need to know what it is. They have the same cross-sectional area. I believe the problem says, let me make sure, the diameter of those is given as little d. All right? So But we don't even need to know that either for this part of the problem. If they have the same diameter, remember the area is pi r squared, which is pi diameter over 2 quantity squared, which is pi diameter squared over 4, and they both have that area. So that's going to drop out. And now, do they have the same temperature difference? No. If we look up the values for K aluminum and K brass, aluminum is 220. And what is brass? 110. And obviously it depends on which type of aluminum, which type of brass, so these numbers might look different in your textbook, blah, 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 blah. Let's keep rocking. Well, let's think about this. You can kind of see what should happen here. The aluminum has twice as much K, so it probably needs half as much delta A. So just kind of eyeballing this, you can probably tell that this one should be 33.3 and this should be 66.7. So we're expecting the temperature of the junction should be about 33 here, but let's go through the math and see. Let's say you didn't understand that, or maybe these numbers don't exactly match up, but we're expecting one of them to have twice the temperature differential. So this should be about a third of the total temperature difference. All right. So in this case, let's work this out. I'm going to say, let's go this way. Ka times the temperature difference would be temperature at the junction minus 0. Right? The temperature difference across here would be Tj minus 0C. And let's put this in purple so it pops. On the other side, let's be careful here. The temperature difference for this one should be high minus low is T hot minus Tj, which would be, I guess if you wanted to do this, and this could be T cold. A lot of times teachers do this algebraically on tests. Give me a second. So this is what it would look like algebraically if your teacher wants you to do that. And then we could plug in this particular case, this is 100 degrees Celsius. And this one, like we said, was 0 degrees Celsius. So yeah, if you had to do it with numbers, there you go. If you had to do it with variables. So now what are we trying to do? Ka Tj minus, oh, that's the only term on this side. Well, let's do it. Moving these Tj terms together, you get Tj times Ka plus Kb. You can erase me. Moving this one over here, we get Ka T cold plus Kb T hot. Now I can divide through by this. And you plug in the numbers. When we plug in the numbers, this one goes to 0, whoops. And then you punch in some numbers here. I can tell that the units on Kb are going to drop out. So let's see, brass is 110 times T hot, which is 100, divided by the quantity Ka, which is 220, plus K brass, which is 110. And I get 33 points. Remember, this is 100. This one is 110. And this one was 220. All right. Was there a part C to this? How would the junction temperature change if we double the length of each rod? Think. Pause the video if you want to take your guess. I'm doing it in 3, 2, 1. Okay, if you double the length of each rod, the junction temperature doesn't change. Does anything change if you double the length of the rod? Well, yeah, the amount of heat transfer will change. So the longer the rods are, you're changing the amount of Q per unit time. So if you want to transfer a certain amount of heat in a short amount of time, you want to use a short length, right? So doubling the length does have an effect, but it will not affect the temperature of this junction in this problem. All right, that's enough. But there's more problems in the workbook like this. Try a couple.